If you're watching this video, then at this point you are going to be an expert in the history of the metric and the imperial A4 paper scales. What we're going to do now is we are going to give a quick example of scientific notation being used in addition and subtraction and multiplication and division. So what I'm going to do for addition and subtraction is I'm going to write out 3 rules that we're going to follow, but I'm going to follow that up with an example if this seems somewhat ambiguous. So when we add or subtract numbers written in scientific notation, we're going to rewrite or convert each individual number so that each term is multiplied by 10 raised to the same power. After that, we will add or subtract the numbers in front of each power of 10. And after that, our answer is going to be the number we found multiplied by 10 raised to whatever power we chose to raise it to in the first step here. So, as an example, how would we add these numbers together? Well, the way I'm going to think about this is I notice 10 to the 4 and 10 to the 3 are not the same power of 10. I want them to both be the same power of 10. So I'm going to rewrite the first term, 3.7 times 10 to the 4, as 37 times 10 to the 3. I basically took away 10 from this term and I gave 10 to that term, so I didn't really change anything. So at this point, I will put parentheses around my numbers just to help group them. I could write 37 times 10 to the 3 plus 1.6 times 10 to the 3. I could use the distributive property of mathematics as 37 plus 1.6 times 10 to the 3. If you're not quite sure about this equal sign, just begin with this term and go backwards. So 10 to the 3, factor it in here, 1.6 times 10 to the 3, factor it in next to 37, and get 37 times 10 to the 3. Now that I have these terms in parentheses, they're just numbers, I'm just going to add them together. So I can write that as 37 plus 1.6 is 38.6 times 10 to the 3. And at this point, as far as I am concerned, if you were to write this on an exam, you would be done. If you choose that you would like to write it as 3.86 times 10 to the 4, it looks a little bit neater. It's nice only to have a single decimal point with a single number in front of it. But if you chose to write it in either way, you would receive full credit in both cases. If we are going to multiply numbers together that are written in scientific notation, the rule we're going to follow is 10 to the a times 10 to the b equals 10 to the a plus b. So as an example, let's multiply these numbers together. Now the first thing I'm going to notice is I have just a lot of parentheses here, but everything is a multiplication. So I could remove the parentheses without any loss of generality. After that, we learned in grade school that if you rearrange the order of multiplication, you're not really changing the final result. So I'm just going to group the numbers together, the 5.2 and the 2.8, and I'm going to put the powers of 10 on the other side. And then after that, I'll throw some parentheses in. So I'll group the 5.2 and the 2.8 together. I'll group the powers of 10 together. And then I can multiply these terms individually. So 5.2 times 2.8 gives me 14.56. 10 to the 2 times 10 to the 4. Well, following this rule, 2 plus 4 gives me 6. So I get 10 to the 6. And again, at this point, as far as I'm concerned, this math equation is done. If you decide you want to clean it up, you could write it as 1.456 times 10 to the 7. Both of these numbers are correct. Both of these numbers mean the same thing. So at this point, both of these answers deserve full credit. Finally, for division, if we divide numbers written in scientific notation, the rule we're going to use is 10 to the r divided by 10 to the s is equal to 10 to the r minus s. But what if you have a number in front of these powers of 10? How should we work with that? So as an example, let's say 9 times 10 to the 3 divided by 6 times 10 to the 5. How do I want to think about this division? Well, it'll help me to visualize what I'm doing if I write it instead of divide it as a fraction. So 9 times 10 to the 3 over 6 times 10 to the 5. What I'm going to do next is I'm going to have the numbers in one set of parentheses, and then I'll have the powers of 10 in another set of parentheses. Now, from the rules of multiplying fractions, 9 over 6 times 10 over 10 to the 3 over 10 to the 5. This would become 9 times 10 to the 3 upstairs and 6 times 10 to the 5 downstairs. So I am just rewriting this with parentheses where I group the non-powers of 10 and I group the powers of 10 separately. So after that, 9 over 6 becomes 1.5. And here I very explicitly have a 10 to the 3 divided by 10 to the 5. At this point, I apply this rule, and I get 10 to the 3 minus 5. 3 minus 5 is negative 2, so I get 1.5 times 10 to the negative 2. In this course, when you're going through a calculation and on an exam, you might get some really long digits, but for a rule of thumb, rounding to 3 digits will always be good enough. Don't write out numbers to 20 significant figures. It's annoying to work with. It annoys your grader when your grader is grading your exams. You want your grader to be in a good mood. So, why is this important? Well, here's an example. Light travels at the speed of 299,792,458 meters per second. And as written, this is a very exact number. To show why it is good enough to just round to 3 significant figures in this course, let's take Einstein's famous equation E equals mc squared. Don't really worry about what this equation really means for the moment. Here, c is the speed of light, which I wrote up here. M is the mass of the object, and E is known as the object's rest energy, or how much energy the object inherently has as a result of the fact that it exists. So let's say we have a ball of 2 kilogram mass, and let's plug this ball 2 kilogram mass into M. Let's compare the exact value for the speed of light and an approximation for the speed of light, and let's see what happens. So if I use the exact value for the speed of light and compare that to an approximation, I could say E is equal to 2 times 299,792,458 square, or E is equal to 2 times 300 million square. I plug that number in a calculator. I get these two results. And if I look at these two results, they both have the same number of digits. 17975, 1800 are the first 4 digits respectively in each. And these two numbers are really only about 0.1% different from each other. They're less than that percentage difference. So if C of 3 times 10 to the 8 meters per second is easier to work with mathematically in a problem, which it always will be, and if having an answer less than 1/1000th away from the exact answer is considered good enough, which it always will be, then we might as well just write with simple numbers rather than worrying about having to copy down long strings of digits. Also, if you ever need to go back through a problem, maybe there was a small plus minus sign error or something, it's easier to look at what you're doing if you write numbers that are rounded to the third important digit. So scientific notation allows us to unambiguously compare very different quantities very quickly. The base unit of time we talk about is 1 second. An 80-minute lecture will last about 4.8 times 10 to the 3 seconds. So I see 10 to the 3, I know that means 1,000. So an 80-minute lecture is 1,000-ish times longer than 1 second. Or another way of thinking about it, 80-minute lecture is about 37 minutes longer than 1 microcentury. You are approximately 10 to the 8 seconds old, give or take, assuming you're 20 years old. So you are about a 1 followed by 8 more zeros old. So 100 million seconds old times 6.3, so 6 times that number. About 10 to the 9 seconds ago was the Great Boston Molasses Disaster of 1919. About 10 to the 10 seconds ago, Greenland was first colonized by the Vikings. About 10 to the 11 seconds ago, the oldest known plant still alive just first sprouted during the last ice age. And about 10 to the 12 seconds ago, the human race almost went extinct about 70,000 years ago. This was most likely due to a change in the climate due to a volcanic supervolcano that erupted. I don't know the exact details of this or if that explanation was updated to something else, but this is as far as I know. If we go back even further, let's go back by a power of 1,000 times further. So instead of 10 to the 12 seconds ago, I'm going back 10 to the 15 seconds ago, plus times some change. I could go around riding on a stegosaurus and the world map looked like this. If instead I want to go 3 times 10 to the 15 seconds into the future, or about 100 million years into the future, the world map will look probably something like this. The Amazon is beginning to be flooded, as is the Congo, and the Mississippi River looks more like a Mississippi Bay at this point. You have a new ocean being formed in the Ethiopian Rift Valley. The Mediterranean Sea's no longer there. Africa bumped up into Europe. Australia also crashed into Asia. If we go back 10 to the 16 seconds ago, so a power of 10 times more than this distance, you have interesting multicellular life is first beginning to appear on the Earth. 10 to the 17 seconds ago, you have Earth when it was first being formed in the solar system. And if you remember from a previous video, 4 times 10 to the 17 seconds ago was the Big Bang. It was a little bit after the Big Bang that the universe became transparent to light. So right around after the Big Bang, the universe was opaque or cloudy, light could not travel through it. But then stuff happened, the universe cleared up, and the universe could travel, light could travel through the universe. So this is as far back literally as we can see if you are looking with light. Now, if this was the Big Bang, that means 10 to the 18 seconds ago doesn't exist based on what we know of current modern day physics. This would translate to about 300 billion years ago. It is possible that the universe is infinitely old, and it might be valid to describe a concept of before the Big Bang, because the Big Bang, it's not really correct to say it was the time that long ago when space and time were formed. It's probably more valid to say at that time, 4.32 times 10 to the seconds ago, the distance between every location is 0. When the distance between every location is 0, you'll have really strong gravitational fields, and we don't know how space and time behave in strong gravitational fields. So to fully describe that, you would need a theory of quantum gravity. So we could say a little bit after the Big Bang, we feel confident we know how space and time behave, but time is not really well defined more than 4.32 times 10 to the 17 seconds ago. Still, sometimes we don't always want to keep repeating times 10 to the whatever power, so we do put prefixes in front of numbers. The common prefixes, 10 to the negative 9 means nano, that is lower case letter n. 10 to the negative 6, lower Greek letter mu for micro, times 10 to the negative 3 for milli, times 10 to the negative 2 for centi, and then kilo and giga, times 10 to the 3 and times 10 to the 9 respectively. Sometimes you'll also see mega, which means times 10 to the 6 or times a million. So I could say a red blood cell is 10 micrometers across. That is the same thing as saying 10 times 10 to the negative 6 meters across, or 0.00001 meter across, but saying 10 microns is just easier to articulate. Now, sometimes it's going to be necessary to go from one system of units to another, like the imperial system to the metric system. So after this video, I will have an excessively long video on doing a conversion where I point out a few subtle things. Fundamentally, when we convert, we take a quantity, we take an idea, and we multiply it by 1. And we know that anytime you multiply something by 1, you're not changing it. You're just getting the same thing back out. We're just going to be creative with how we write the number 1.